Okay, so welcome to lecture number 3. We'll continue our review of some fundamental content related to probability and statistics. A quick note, I did introduce some minor edits to the slide deck from the last lecture. Specifically, I removed the slides that we hadn't yet got to. And I'm going to update the syllabus because we've had a few changes. I was going to cover confidence intervals and then hypothesis tests, but I just couldn't figure out a way to sequence that so that it was coherent. So I'm going to start with hypothesis tests over the next few lectures, and then we'll circle back to confidence intervals. I just think it's easier intuitively to cover the topics in that sequence. And so apologies for those of you that were really excited to talk about confidence intervals today. Okay, and so we had concluded the last lecture talking a little bit about statistical distributions, and we talked about 4 different moments of the mean, basically. And so we introduced the variance and standard deviation. We talked about skewness and kurtosis, and we were just about to get started talking more broadly about statistical distributions. So we'll wrap up that content this morning. We'll start introducing hypothesis testing, and that will include some general terminologies as well as detailing a general 6-step process that applies for some of the simple tests that we'll talk about over the next few lectures, and we can extend those same general principles when we talk about developing various types of regression models and doing some more rigorous types of statistical analyses. We have 2 upcoming due dates. So the term paper topic, I'm looking for ideas by the end of this week, and then the plan is to review those over the weekend. And then hopefully by next week, we will have those paper topics finalized. And as a reminder, you're going to need data for the purposes of the term paper. And so in an ideal scenario, you'd have something that you're working on with your advisor. In the event you don't have a data set readily available, there are a wealth of publicly available data sets, and there's also some additional data that we would have access to through either current or prior research projects. So feel free to reach out to me if you've got questions. And then secondly, we'll have our first assignment due a week from Friday, and so that should be going up later today, and more details will be forthcoming, but we'll be using some real world data we've collected actually for an ongoing research project for the purposes of assignment 1. So keep your eyes open for that. Okay, and so at the end of today's lecture, you should be able to basically standardize the variable, utilize a standard normal table, distinguish between the term standard deviation and standard error, specifically the standard error, the mean, but we'll use that term more broadly to talk about the standard error of any parameter of interest. And then you should hopefully be able to explain hypothesis test procedures at a high level, and we'll start applying those in detail on Wednesday. Okay. So first and foremost, anytime you're conducting any type of statistical analysis, oftentimes we kind of rush to start applying statistical tests, but one of the most important first steps is to understand the nature of your data. And typically my first suggestion is going to be that you plot that data in various forms and fashions, okay? Specifically, whatever our dependent variable of interest is, it's nice if we start out with a histogram to get a sense of what those data look like. We talked last lecture about some of the different ways we can assess the nature of that distribution. And, we talked about measures of central tendency like the mean or median or mode of that distribution. We talked about several different ways we can assess the variability of the data with respect to that broader distribution, and that would include things like the variance, which would give us a sense of how peaked that data is in the middle, and to a lesser extent, how much variability there is out in the tails. We talked about skewness, which is a measure of how symmetrical that distribution is. And then fourthly, we talked about kurtosis, which is basically assessing how much extreme values we see out in the tails of those respective distributions, okay? And so there's a few reasons we're interested in what the shape of these frequency distributions look like. In large part, if our data are well represented by various types of standard distributions. It introduces some advantages to us from an analysis standpoint because we can use information we know about the properties of those distributions. And if they're well aligned with our own data, it helps us to make inferences with relatively high levels of precision. And so we'll talk a little bit more about that as we move forward. But just looking at this, so this is basically a bar chart. You've seen it many, many times. And you'll notice here, we can refer to this as a frequency distribution, or you'll see on the exterior axis there, a relative frequency distribution. And so can someone just kind of distinguish for me what the difference between a frequency distribution and a relative frequency distribution is? I guess feel free to type it into the chat box, or if you're shy, or unmute yourself. And so frequency distribution, real quick, real easy. What is that?
The frequency distribution is how many of each observation you have in the data.
Yeah, so with a frequency distribution, all we're doing basically is we're establishing ranges for our data, and then we're just indicating how many observations fall within each of those ranges, right? And so if we take the frequencies for each of these bars, this would tell us, for example, there's 2 observations that fall between 70 and 90. There's 3 that fall between 90 and 110, and so forth and so on. And then as we transition to relative frequency, all we're doing there is taking this frequency distribution and dividing by whatever our total sample size is. And so that's then going to convert these values to probabilities. Okay, so if we sum the area underneath this relative frequency distribution, that would sum to 1.0, right? It would break that sample into the relative proportions that fall within each of those respective categories. Okay. And like I said, in many cases, one of the advantages to that is we can think about that probability distribution, that frequency distribution, and oftentimes they tend to follow very nicely some standard statistical distributions for which we have known properties. And since we have known properties, there are some calculations we can conduct based upon the properties of those distributions that allow us to then try to address some research hypotheses of interest, okay? And so as we look at that frequency distribution down here, you'll notice that it is very similar in nature to the shape of a statistical distribution. And so we'll introduce some general terminology here. And so we have what are referred to as probability density functions, and that's what you see basically on the top here. In this specific example, this is showing us what a normal distribution looks like. And so there are 2 parameters that define the shape of the normal distribution, and that's the mean and the standard deviation. And so for any given sample, if we have those quantities and we can assess whether or not those data are approximately normal, then we would have a sense based upon our estimates for those population parameters. So we can estimate our sample mean, X bar is going to give us an unbiased estimate of mu, and likewise S, our sample standard deviation, is going to give us an unbiased estimate of sigma, which is our population standard deviation. And so we can use the mathematical formula for the probability density function to determine how likely it is that values would fall within certain ranges, as an example. And so what we see over here, this is just replicating what that probability density function looks like. And so if we integrate over this function up to a given point, that would just simply give us the probability of a value falling within those specific ranges, okay? And so that relates naturally to the figure below it, which is a cumulative distribution function. And so the probability density function is basically telling us how likely it is that we would obtain values in specific ranges here. And in contrast, what's the cumulative distribution function telling us, John K?
So you're just adding up the probability rather than looking at it sort of, I don't know how to word it exactly, but instead of looking at the whole thing, you're just at the cumulative essentially.
Yeah, so all we're doing here is we're basically integrating this function. We're taking the cumulative percentage or proportion of that data set that is less than or equal to these respective values, okay? So it may or may not be obvious from looking at this, but we're very flat out here. Probability is very low. Likewise, this probability is very low. And then as we start to get to the interior points here where there's a large cluster where most of our data points lie, we start to rapidly increase our probabilities here because that's where the large cluster of those points are occurring. And then as we get to the more extreme values, as indicated here, or on the higher side, the larger values in this distribution, that starts to taper off again, and we're asymptotically approaching 1 as we get to our extreme high values in that case. Okay, makes sense? Okay, and so the most widely utilized distribution is referred to as the normal distribution, and hopefully we're all relatively familiar with the normal distribution. It's often characterized by its shape. Does anybody recall what shape we generally refer to the normal distribution as?
Bell-shaped?
Yeah, so basically we got a bell-shaped curve, right? And so this is, like I said, probably the most widely used distribution for statistical applications. And in order to determine the specific shape of that normal distribution, we need to define 2 parameters, the mean and standard deviation. And what the mean is going to do is it's going to vary where that distribution is centered as we look at the number line. And the standard deviation is going to give us an assessment of how high the peak is and essentially how fat or narrow the tails of that distribution would be. And so if we know what mu and sigma are, we can then determine what the probability is of us taking any specific range of values over that normal distribution. And so you'll see a few probability density functions illustrated here. And what you'll notice in looking at this, as I had indicated, mu is simply telling us, that mean is telling us where that distribution is centered. And so 3 of these distributions, the blue and the red and the yellow, are all centered at 0, as you see right here. In contrast, the green distribution is centered at -2. And then as we think about the relative shapes of these distributions, and this should make sense intuitively, as our standard deviation or as our variance gets smaller, what's tending to happen to these distributions in a qualitative sense? So what happens to the shape as our variance gets smaller? Yeah, so it's basically getting narrower. And if you think about this as if there's an underlying frequency distribution beneath this, you'd have a large cluster of points right around the mean if we had a sample with low variance, right? If we had a sample with larger variance, we'd have a lot of those bars would be higher as we get out to the extremes here. And so a low variance distribution is indicated by the blue example you see right here. A high variance distribution is indicated by the yellow here, where we have much more uniformity in terms of the range of values that are taken here. And so consequently, even with a normal distribution, it's always going to take that general bell-shaped curve, but the actual shape can vary significantly depending upon the variance. And then, like I said, the location also varies depending upon the mean of that distribution, okay? And so there's one specific normal distribution that's of particular interest to us. And what's that distribution? Everybody hopefully knows this one. Anyone? What's our, yeah, exactly. So the standard normal distribution. And what's special about the standard normal distribution? What is the mean of the standard normal equal to? Anybody? All right, I'm seeing a lot of zeros pop up in the chat box. Thank you very much. And the variance or standard deviation of that normal distribution is equal to what? Right. So standard normal distribution is just, we take the normal distribution that was shown in the probability density function on the preceding slide. We plug in 0 for the mean, 1 for the variance, and that's basically the standard normal. And oftentimes we refer to a standard normal random variable as Z. So we denote that by Z. If we know the mean and the variance of the population from which a variable is drawn, we can then determine how likely it is that we would find a value of any particular number, which we'll just denote here as Z, okay? And so the cumulative distribution function for a standard normal random variable is of particular interest to us. And so you've likely seen capital phi of Z here, which is basically just telling us the cumulative probability of observing some number less than or equal to Z. Okay, so as we read across that normal distribution, and we also denote that same quantity as capital F of Z. And one of the most common applications we'll see in introductory stats is we can basically take any variable from that distribution. So we can just denote that as X, for example, and we can subtract off its mean, divide by its standard deviation. And what that's doing is basically standardizing that variable. And so with that, we can basically use a standard normal reference table that will tell us how likely it is we would have a value that's that large or that small, basically that extreme relative to where the center of that distribution is located. And that'll probably be best demonstrated through an example here. But anyway, phi of Z or F of Z is basically quantifying the cumulative proportion of that distribution that's less than or equal to some point, which as I indicate here is denoted by Z, okay? And so if we look at these tabular summaries here, this is basically telling us what the respective cumulative probabilities are for ranges of that value Z. So if we think about Z, we're taking any observation, we're subtracting off the mean, and we're dividing by the standard deviation. So in practical terms, if we calculate Z and it's equal to 1.0, that would basically tell us that that specific value is one standard deviation greater than the mean for that respective distribution. Okay, likewise, if we calculated Z and we found it was equal to -2, that would indicate that we were 2 standard deviations less than the mean, for example. And so we can just simply read across these respective tables. And from that, you can determine, as an example, a value of -2, there's a 2.28% chance. So these are probabilities here, 0.0228. So slightly more than a 2% chance that we would obtain a value that's less than or equal to -2. And likewise, on the other side, there's an 84.13% chance we would obtain a value that's less than or equal to 1. We could also, using the same table, then determine the probability of a number being greater than 1 as an example. And so that would just be 1 minus that quantity, so 0.1587 as an example, okay? And so let's just do a nice simple example here where we're illustrating the use of the standard normal distribution. And this will actually build up to the homework assignment where we'll be working on some speed data that's been collected throughout the state. So let's assume we have speed data that's been collected from a distribution, and we know that the mean value of those speeds, if we were able to observe every vehicle, that mean is 55 miles per hour. And the standard deviation of those vehicle speeds is going to be 5 miles per hour, okay? And so with that information in hand, we want to know how likely it is if we were to observe an individual vehicle that its speed would be greater than 70 miles per hour, okay? And so in this case, it's just a nice, simple, straightforward application of that standard normal formula. So Z is equal to X. So X is basically the specific value from that distribution that we're interested in. In this case, we're interested in how likely we would obtain a value as high as 70 miles per hour. We subtract off our mean of 55 miles per hour. We divide by our standard deviation. And we find that our calculated Z statistic is 3.0 in this case. And so that means that that 70 mile per hour vehicle is basically traveling 3 standard deviations above what the average speed of vehicles from that distribution is. Okay, so that's a relatively high value. How high? We can basically go directly to our standard normal table over here. And so you read down, and so just to reorient everyone here, we're reading down to 3.0, and then as we read across, this is just taking us to the 100th place, so 3.00, 3.01, 3.02, so forth and so on. In this case, as we read across, we see that our value is equal to 0.9987. So 99.87% of all observations would be less than 70 miles per hour. And so consequently, if we wanted to figure out the likelihood of being greater than 70 miles per hour, we just take 1 minus that difference, which would give us 0.0013. Okay. Everybody with me up to this point? Just feel free to give me a thumbs up or wave your hand or whatever the case may be. If at any point here you need to interrupt, just feel free to type a message into the chat box so you can interrupt audibly there, and I'll make sure we're all on the same page, because we're going to continue to build upon these fundamentals that we talk about later today. Okay. Likewise, we can use that same approach to determine how likely it is we would fall within a specific range of values. And so with the same information in hand, if we assume a mean of 55 miles per hour, a standard deviation of 5, how likely is it we would observe a speed between 50 and 60 miles per hour? And so to approach this, we're basically going to use our standard normal formula here to convert each of those values to its corresponding cumulative standard normal value. And so 50 minus 55, the numbers here are nice and straightforward. So we're basically 1 standard deviation below the mean in this case. And with that information in hand, we're basically going to the other half of that standard normal table. And so if we read down to negative 1.0, we see there's a 0.1587 probability that we would be less than that value. Likewise, so everybody's clear on this, if we were looking at the other extreme and this was positive 1.0, we'd have that same probability of being greater than positive 1, okay? Because the standard normal distribution and all normal distributions are going to be symmetric. So we can take the number that's less than that lower value or greater than that higher value, and we get the same result there ultimately, which will be demonstrated in just a minute here. So our probability of being less than or equal to negative 1 is 0.1587. And so that gets us part of the way to where we want to be here, but we're not interested in values that are less than 50 miles per hour. We're interested in values that are greater than 50 and also less than 60. So the next step here, we take that 60 mile per hour observation, we subtract off the mean of 55, divide by the standard deviation, and now we're 1 standard deviation above the mean. And so reinforcing that fact, this is the other half of the standard normal table again. We read down to 1.0, and here we see that 0.8413. So there's an 84.13% chance we'd have a value that's less than or equal to 1.0, or a speed that's less than or equal to 60 in this case. And as before, you know, the probability of being greater than that is that same number we saw previously, the 0.1587, given that the numbers are nice and symmetric here. And so we know how likely it is that we'd be less than or equal to 50 from this first calculation. We know how likely it is we'd be less than or equal to 60 from this second calculation. And so to pull that all together and find the probability of being between 50 and 60, what's the next step we need to take?
P1 minus P minus 1.
Yeah, exactly. So we want the value between those two. And so we're just going to take the 0.8413 minus 0.1587, and that's going to give us the probability of being greater than 50 and less than 60, okay? I should note I'm getting a little bit sloppy here in terms of how I'm stating that. So that the probability of being equal to any specific value is essentially 0 for practical purposes. So if I ask the probability of a speed being greater than 50 or greater than equal to 50, we would get the same result in applying the standard normal table in those cases. I don't want to go too deep into a rabbit hole here, but that's generally a safe assumption, although we'll talk later in the class about specific circumstances where we may run into issues with that. But for all intents and purposes, we're not particularly concerned with whether that's greater than or greater than equal to, for example, okay? All right, one other point I wanted to bring up really quickly is the term standard error. I guess quick show of hands, how many of you are familiar with the term standard error? Does anybody care to give me a quick and dirty definition of what standard error means? I'm sure all the hands will go down very promptly now. So the standard error is basically just the standard deviation of a sampling distribution for a statistic. So we often think of those terms somewhat interchangeably. So when we're estimating a regression model, for example, we're typically trying to figure out what the parameters are, what the effects of variables are, but we're also interested in the standard deviation of those effects. And so we refer to that as the standard error of the parameter, for example, okay? Now, the most common case we'll probably encounter for standard error is the standard error for the mean. And so as we talked about last time, the sample mean is basically an estimator of the population mean. So X bar is used to estimate mu for the population. And if we think about it in concept, let's assume we're taking a lot of different samples from a given population. So we go back to the vehicle example, the vehicle speed example we were just working through. And so in that case, we could sample speeds of 10 or 20 or 50 or 100 or 1,000 vehicles. And what we would likely find is that each of those distributions would have a slightly different mean speed, right? And what we would tend to find is we would get more reliable results, or we would get results that are closer to whatever the actual mean is, the more data we collect. And hopefully that makes sense. If you just sample 10 vehicles versus 100 vehicles versus 1,000 vehicles, all other things being equal, we would be more confident in the estimate we obtained from that sample of 1,000 vehicles versus that sample of 10 vehicles, right? And so we can quantify how precise that estimate is using the standard error formula we see right here. Okay, so the standard deviation specific to that mean value. So this is basically telling us if we kept drawing repeated samples, this is how much variability there would be within those repeated samples if they were all randomly drawn from the population. And so all we do in that case is just take whatever the standard deviation is that corresponds to that data set. So in the preceding example, we had a standard deviation of 5 miles per hour for vehicle speeds, and we divide by the square root of n. And as you can likely see from this, then the consequence of that is as n gets very large, the standard error term gets very small. And so if we think about that in terms of a statistical distribution, as our sample size increases, that distribution starts getting much narrower, and we're able to hone into a much narrower range of values and have a lot more confidence in terms of the prospective values we would see for that mean based on the sample data we've collected, okay? And so as I had noted, there's an interrelationship between the standard deviation and the standard error of the mean, but it's important to document a few facts, specifically as it relates to how these are calculated and when and if sample size matters. And so the standard deviation is basically, as we think back to our formulas from last Wednesday, the standard deviation is just going to be equal to, so in the case of a sample standard deviation, S is equal to the square root of summation of xi minus x bar, that quantity squared, all over n minus 1. Okay, so we take the square root of that quantity, and that gives us a standard deviation, and that's going to be the same, generally speaking, regardless if we have a sample of 10 observations, 50 observations, 50,000 observations. So regardless of how large the sample is, you're going to see that same value, it's going to be unaffected by how large the sample is. Now, with that being said, I don't want to confuse things here. You would have an estimate that's closer to the actual mean the larger that sample is, but the actual variability, so that sample standard deviation, isn't going to change regardless of what our sample size is, okay? So from a big picture perspective, it's just telling us how much variability inherently there is in our data, okay? So if we look at things like vehicle speeds, you're gonna see significantly more variability in vehicle speeds than you will in things that are very stable, like let's say if you looked at median income or gross domestic product, or things that tend to change very incrementally. And so, as I had alluded to, each of those individual samples you draw is going to have a different standard deviation. But as the sample size increases, that parameter is going to stay the same, okay? In contrast, for the standard error, the mean, this is telling us what the standard deviation of that sample mean is. And so what's going to tend to happen is as our sample size gets larger and larger, we're going to tend to converge towards the actual population mean. And as a consequence of that, the larger our sample size is, the more accurate that estimator is in simple terms, okay? And so the big takeaway here is basically that sample size isn't going to influence our standard deviation, but it is going to estimate our standard error. And we'll talk about this a lot more as we start getting into hypothesis testing. But the standard error is going to be critically important for each of the statistical tests we'll talk about over the next 2 weeks, okay? One somewhat related factor or item of interest is what's referred to as the central limit theorem. And I'm not sure the degree to which any of you may recall this from prior stat classes. Just for fun, let's see, show of hands and thumbs. How many of you recall the central limit theorem? Okay, not as many hands and thumbs going up this time. So the central limit theorem basically tells us that if we have a sample that's sufficiently large, and that sample is drawn from a population with a finite known variance, the mean of all the samples that are drawn from that population will be approximately equal to the mean of the population. And that's going to hold true regardless of what type of distribution those data are drawn from. So if it's drawn from a normal distribution or a uniform distribution or a binomial distribution, and I could just keep rattling off distributions, I guess, here, but probably the best way to work through this is to just demonstrate in simple terms. Let's assume we're going to throw dice and we want to know what the average score from throwing those dice would be. So I'm not sure how big of gamblers we are necessarily in the room here, but if we're throwing die, you can get a value between 1 and 6. And what's the average value we'd expect to see from a single dice throw? Anybody? So the numbers range between 1 and 6. You have a 1 in 6 chance of obtaining any of those values. So what would our mean estimate if you had to bet your life on what the next dice roll? Well, let me not put it that way because you'd be wrong if we're just rolling one die. But what's your best guess? What would be the most accurate guess as to what the value you'd expect to see? It's not an integer. Let me, yeah, so 3.5. Thank you, Jordan, Asan. Emma, you were thinking in the right direction there. Probably it's going to be either 3 or 4. But in this case, if you just think about what that distribution looks like, if we're rolling one die, there's a 1 in 6 chance that we would get a 1, a 2, a 3, so forth and so on. Okay. And so if you calculate the average there, you basically summing all these up, dividing by the total probability, and it's going to put you right at 3.5. Now, if we roll 2 dice, what's our best guess of that average going to be? I will pretend all of those numbers were just typed in a second time. It's again going to be 3.5, right? Although the possible combinations are going to be different here because if we're rolling 2 dice, there's going to be just that one chance that we would get 2 1s. There's the one chance that we would get 2 6s. And it's going to be much more likely we'd come in the middle here near 3.5, because there are different ways we could get 3.5. You know, you could roll a 3 and then a 4 and then a 3, so forth and so on. And as we keep adding dice, our number of potential outcomes is going to change. And with that, the shape of that distribution is going to change. Okay, so any one independent dice throw, you're going to have just this uniform distribution, which doesn't look anything like a normal distribution, really. But as we start increasing the number of samples we're taking, or increasing the number of dice rolls in this context, it's going to very rapidly start to approach a normal distribution, as you can see here. So as we go from 1 to 2 to 3 to a sample size of 5, we're getting very close, and up to 10, that looks, you know, very much like a normal distribution, okay? And the same phenomenon is going to hold regardless of what your underlying distribution looks like, as long as we have a sufficiently large sample, okay? And that's going to be very advantageous to us if we think about this from an analysis standpoint, because that means it's going to be relatively straightforward for us to obtain reliable estimates of what a population mean is going to be equal to, okay? We just need to make sure we collect enough samples, essentially, okay? All right, so at this point, we're going to start talking about hypothesis testing. We'll see how far through things we can get here today. But again, real quickly, show of hands and thumbs. How many of you are familiar with hypothesis testing? Okay, thank you. There are a lot of hands and thumbs going up there. Okay, and so basically, a hypothesis test is a method we use if we're trying to investigate a research question of interest, and we'd like to be able to draw inferences regarding some parameter of interest, okay? And so typically, we would conduct hypothesis tests in scenarios where we might want to make comparisons between different groups, or comparisons between a single group and some reference value of interest. And so if we think about the speed example, and this will lead up to the homework we'll be talking about, in that case, one of our hypotheses may be, you know, whether or not the speed limit increases that occurred in 2017 had a meaningful impact, or whether those speed limit increases led to any differences with respect to whatever the historical mean speeds were. There are different ways we can try to frame that. But in a hypothesis test, we're basically trying to outline some statement about a parameter of interest we're interested in investigating. And from that, there are a series of processes and tests we can conduct in order to come to a conclusion about the nature of that parameter that we're interested in investigating, okay? So basically, we're gonna develop a null hypothesis, and that null hypothesis is basically going to be that there's no effect, or there's no difference, and we'll talk a little bit more about why we set it up in that manner. And we're going to compare that null hypothesis to an alternative hypothesis, which could be, for example, that the parameters are different between those two groups, or the parameter is larger in one group versus another. And so if we think back to Friday's transportation seminar, and a quick note here, I'll plan to post details of all those seminars, because I think it'll provide some useful discussion points for the purposes of our course. And I think, ironically, our speaker from Friday's seminar was showing up as a guest here today as well. But so on Friday, our seminar essentially focused on what the impacts of COVID-19 and the associated travel restrictions were on how much people travel, okay? And so if we think about that from a hypothesis testing standpoint, there are different ways we could try to formulate a hypothesis there, but essentially what we're trying to determine is, did the introduction of the travel restrictions due to COVID have a meaningful impact in how much people traveled? And so to assess that, what we basically did is we collected data after those travel restrictions went into place. We compared those data to similar data that quantified the level of travel before the restrictions went into place. And so on that basis, our null hypothesis would basically be that there was no difference between the amounts of travel that occurred pre and post COVID. And the alternative hypothesis there would be that there is in fact a difference, or specifically that the travel levels went down after those restrictions were introduced in the stay-at-home orders. Okay. All right. And so as we think about this from a big picture perspective, that's essentially going to be our first step in hypothesis testing, is we're going to define the null and alternative hypotheses of interest. And so, like I said, that's going to generally mean that we're selecting some parameter or parameters of interest that describe the population we're interested in, whether that's the population of drivers and how fast they travel, or the population of drivers and how much they travel, for example. We're going to establish a significance level, which is basically setting a threshold that relates to the risk and uncertainty that's inherent in our testing procedure. We'll collect or somehow obtain data in order to evaluate that hypothesis, and those data can be used to calculate summary statistics like the mean and standard deviation and so forth. And those values can be plugged into various test statistics. We compare that test statistic to a critical value, and then based upon how those values compare to one another, we can draw conclusions and inferences based upon the results of those tests, okay? And so the remainder of today's lecture, we're basically going to just step through these different sequences in the process of hypothesis testing, okay? So first of all, like I said, the null hypothesis is basically a statement that we're trying to disprove, is how we can think about this, okay? So oftentimes we start these intro courses with doing nice simple tests just about means of populations. And so, for example, if we think about either the speed example or the COVID travel example, our null hypothesis would typically relate to, let's say, some population mean mu. So mu could be our average travel speed, or the average amount we travel. And we're going to assume going in that that's equal to some reference value. And so, for example, let's stick with the COVID example. If we took the mean number of miles that people traveled after COVID impacts came into play and compared that to some reference value, so the mu naught, this naught is just indicating that this is some reference value of interest to us. So we're going to assume that it's just equal to some reference value. And in this case, the reference value would be the amount of miles that people traveled prior to those restrictions being introduced, okay? And so subtle differences in terms of how we set this up. So we could also think about this as if these were two independent populations. So mu1 is basically the mean of all the travel that occurs during period 1, so pre-COVID, and mu2 is an estimate of the mean travel, how much travel occurred post-COVID, okay? And as we start getting into some of the specific tests on Wednesday, we'll delve into some of those differences in greater detail in terms of when we'd select one of these versus the other. But those are different ways of trying to assess the same research question of interest, okay? Now, with that being said, there are alternative hypotheses to these respective nulls, and those are basically as you see indicated here. So we can either just test for whether or not there's a difference between that population mean and the reference value we're concerned with, or with differences with respect to the means of those two populations. Or alternately, going into the test, we may have some prior information, or we may have some thoughts as to a potential direction we're expecting to find in terms of the nature of those effects. And so let's say, as an example, in the case of travel speeds, when the speed limits are increased, we would probably expect that the mean speed of all drivers would be greater than whatever that prior reference speed was, as an example. Okay, so let's assume mu here is the speed after the increases went into effect. Mu naught was the prior mean speed. we may expect the relationships in this direction. Okay. Similarly, in the case of the COVID travel restrictions, we would probably assume going into that we're probably unlikely to see the same levels of travel, and we're probably thinking going into that travel is going to be reduced by some amount, and we're just trying to figure out whether or not that reduction is statistically significant in essence. Okay, so we may assume alternately that we would have this direction in terms of that relationship as well. Okay. And so as a part of that, we basically set up these hypotheses, and we're setting them up such that we're going to work to basically disprove the null. Okay, so in this case, we're trying to collect data and ascertain whether or not speeds actually did change, or the amount of travel people have done did change as a result of either the speed limit increases or the imposition of stay-at-home orders. Okay. And so when we conduct these tests, the way it basically works, we collect sample data and we conduct tests using those sample data, and then we draw inferences from those tests. Now, as it would turn out, these tests and these data are stochastic, they're random in nature. And so as a consequence of that, even if there is an actual difference or there is an actual effect between these groups, or with respect to whatever policy change or whatever item went into effect there that we're trying to evaluate, there's going to be simply a likelihood that we find a difference when there actually isn't one, just given the nature of sampling. Okay, so if we think back to that normal distribution, we may just happen to draw a sample that's up in the high end of that distribution or the low end of that distribution, just due to bad luck from a researcher's perspective, essentially. Okay. And so we refer to what's known as a significance level. We'll also see this referred to as alpha. And so what alpha means is it's basically telling us the probability that we would reject the null hypothesis when it's actually true. So within the context we've been talking about up to this point, that would mean that we found that speeds changed after the speed limit increase when that wasn't actually the case, or that travel levels changed after the introduction of stay-at-home orders, when in fact maybe they didn't. Okay. And so the significance level is basically something we establish as researchers at the onset of our study. And this is basically establishing a level of risk that we're comfortable with. Okay. So it just so happens that, like I said, based on sampling theory, sometimes we're just going to get unlucky with our samples. And so that's going to happen no matter what. And so we need to establish a threshold in terms of how often we would be okay with that occurring, basically. Okay. And there's not really a great background in terms of why we use specific values of alpha. And to be perfectly frank, we basically have historically selected numbers that are relatively nice, or common numbers, with our most common alphas being like 0.05 or 0.01. And so in those cases, we're basically saying we're willing to accept the fact that there's a 5% chance or a 1% chance that we'll find that a difference exists when in fact it doesn't. Okay. And now this can lead us down a very slippery slope, because depending upon the nature of the research question we're investigating, the possibility of us committing what's referred to as a type 1 error. So when we reject the null hypothesis, when that null is actually true, we can refer to that as a false positive, essentially. Okay, so we're finding an effect that isn't actually there. And in certain contexts, that can be really problematic. And I think a good example there is now there is a lot of money and time being spent trying to establish a COVID-19 vaccine, as an example. Okay. And so there's been a lot of extensive testing done to try to determine whether or not these vaccines are effective in mitigating the likelihood that that disease will be contracted and spread and so forth and so on. Okay. So if we conduct all these tests, we'd probably want to set them up such that we're minimizing how likely it is that we would find the drugs to be effective when in fact they're not, right? And so in that specific case, it probably wouldn't make a lot. I wouldn't be very comfortable if you're giving me a vaccine and you say that alpha is, you know, 0.1 or 0.05. So, you know, if there's that high of a chance that it's just, you know, the results we've seen to this point are due to randomness, that's a pretty big concern. So in those types of domains, you know, medical testing and things of that nature, we'd probably want to establish a significantly lower threshold and make it more difficult for us to reject the null, because we don't want to do so falsely, okay? And we'll talk a little bit more about this on Wednesday when we start applying some of these statistical tests. In contrast, if we're focusing on a research question that doesn't have the dire consequences that we see for something like a vaccine in the case of committing a type 1 error, we'd probably be comfortable with a higher number, with a 0.05 versus say a 0.0005 or whatever the case may be in some of those medical testing procedures, okay? And so from a big picture perspective, what this means is we're going to calculate a test statistic based on that significance level, okay? And the more extreme that test statistic is, so if it's disproportionately large or small as the case may be, that's going to be the circumstances under which we would reject the null hypotheses, okay? So like I said, though, even we set this up so that under the assumption that our null hypothesis is true, in actuality, that null, it could be true, and we could just end up rejecting it just based on the fact that we happen to draw a random sample that was out in this region right here, okay? And so what we're trying to do at the onset of the test is basically determine how large that region should be. And so if we want to be more stringent, we basically make alpha smaller, so we minimize our probability of falsely rejecting the null. And what that's going to do in consequence, it's going to push this critical value out further, which means we're going to have to observe a larger difference in order for that null hypothesis to be rejected. And there are implications to that as we think about designing a research study. We can kind of back calculate, and we'll talk about this later in the semester as well, how much data we would need in order to reject a null hypothesis under certain circumstances. But that can be somewhat of a slippery slope as well, because one kind of dirty trick in statistics is that if you increase your sample size, you can increase it to such a degree that even very, very small, meaningless differences can be shown to be statistically significant. So it's somewhat of a balancing act here, but in practice, for most applications, we'd set alpha equal to 0.05 or 0.01 for our common transportation applications, okay? And so, like I said, just to reiterate that, if we say that our significance level is 0.05, it means there's a 5% chance that we conclude the null is false when it's actually true, okay? Everybody okay up to this point? Okay. All right, and then the next step would simply be to collect data, and there are a wide range of ways in which we could do that. And I guess let's just check how we're doing time-wise. We're okay on time, and so let's think first of all about the speed example. So let's assume that we have increased speed limits, and we're going to conduct a research study. In an ideal world, we would go out and we would measure speeds before the limits were increased, and we would come back and measure speeds again after the limits were increased. Now, in the simplest case, let's just say, well, we went out, we observed 100 vehicles back in March of 2017 before these increases went into effect. And then we went out and observed 100 more vehicles last week. And so on that basis, I'm going to make a determination as to whether those speed limit changes had impacts. Are there any problems with that approach? Does anybody have problems with me determining the effects of speed limits by measuring 100 vehicle speeds in March of 2017 versus 100 vehicle speeds in January 2021? Okay, so Nishal's indicating there's a time factor. Do you care to elaborate on that a little bit, Nishal? What do you mean by a time factor?
Like with time the speeds would tend to uh, stabilize.
Okay, so I think what you may be talking about there is there's maybe a potential, we can refer to it as a novelty effect, or there may be some driver adaptation or learning over time. So once those speed limits are increased, there's a few things that could conceivably happen. Drivers may be slow to react to that. So maybe initially when data are collected, we don't see much in terms of increases, but maybe drivers will tend to increase their speeds over time. In contrast, maybe people get anxious, and we could actually see that people had started increasing their speeds before the limits even went up, as an example. And so these increases in 2017 occurred sometime between March and November, depending upon the area of the state and the facility type. And so time plays an important factor in several different ways there. Beyond just when these observations were conducted, any other concerns about that simple study design I just articulated? I guess continuing on the time point, does anybody have reservations with us conducting the initial observations in March and the subsequent observations in January? And if so, please feel free to type just a few short sentences into the chat box to that effect, or unmute yourself. Yeah, so there are a few different things that happen here. So seasonal traffic variations, and could mean several things by that. So, and another great point, the weather. And so anytime we're collecting data to try to address one of these research hypotheses of interest, in an ideal world, we'd like to conduct this as a designed experiment where everything is exactly the same except whatever that one change is, that one difference is that we're trying to assess the impacts of, okay? In the case of the speed limit increase, we'd like for everything to be identical except now the speed limit's higher. Okay, now as a consequence, there are a whole bunch of other things that could potentially come into play here, and we're not going to be able to conduct that as a designed experiment. In the best case, we can do it as an observational study. We go out, observe traffic before and after, and then as long as those contexts are very similar, we're probably going to be reasonably okay there, but there are a wide range of things that could happen. And if we did the pre-increase observations in March, compared to January for the post observations, we'd probably see lower speeds, I would presume, in January because the weather's going to be a bit more adverse. And so if it's snowy or icy out, people are likely to reduce their speeds. And interestingly, in this context, then if people are naturally reducing their speeds, that would tend to underestimate the magnitude of that speed limit increase, as an example. Okay. Likewise, several of you cited traffic variations. And so that would probably make a lot of sense as well. If you have higher levels of traffic volume, speeds are going to tend to be lower as a consequence of that. Even when we're selecting the speeds of vehicles to observe, and I know not everybody here necessarily has extensive background in traffic engineering, but when we're trying to conduct speed studies, we generally try to select speeds of free-flowing vehicles, so vehicles that don't have another vehicle immediately in front of them. Because if they have a vehicle immediately in front of them, we're not getting a good sense of how fast those people would drive of their own volition. Their speeds are constrained by other motorists, okay? Outside of that, you know, hopefully we're conducting those observations on the same roadways during the same time of day, but just whenever we're setting out to develop a data collection plan, we want to think about how we try to isolate whatever the effect is for the item of interest we're trying to investigate. So in this case, it's going to be a speed limit increase or the introduction of stay-at-home orders. We want to try to make sure that everything else is the same except for those items. Now, from a practical purpose, you know, like I said, this isn't an experiment, so we don't have control over all of these factors, but we should at least be able to quantify some of that information. So if we at least note that, you know, some of the observations occurred in March while others occurred in January, we could look at historical differences between those time periods to try to see what sort of variability we may see as a consequence. We can try to control for some other localized factors that may play a role here, but you want to be careful not to think just about whatever it is you're trying to evaluate the effects of. You want to think of all the other things that could introduce noise or random variability to our data, and we want to be able to preferably control for those factors, but in the worst case, at least document those, because oftentimes information about the context in which our study is conducted can be as or more important than the actual results we get from statistical tests, okay? So that was probably about the most talking I'll ever do on a one-sentence slide, if I'm remembering how I've got these set up here. But once those data are collected, there are numerous statistical tests that can be conducted in order to evaluate that hypothesis of interest, okay? And so the tests that we'll start with over the first couple weeks of the course will largely focus on means, because oftentimes the means of populations are what we have the greatest interest in. And when we're comparing means, there are actually a wide range, or let me clarify that. Not even just means necessarily, but we're interested in assessing values of central tendency. So where the expected value or the most common or expected values of a distribution would lie. And I bring that up because if a distribution is skewed, there may be reasons we would compare the medians rather than the means. But the general approach is similar here. And so when we're comparing means and the variance is known, we would use what's referred to as the z-test, okay? And the z-test is very similar to what you saw when we introduced the techniques for standardizing random variables previously. Now, practically speaking, the variance is virtually never going to be known to us in practice. And the reason for that, as we talked about last Wednesday, is that we're not observing the entire population, we're observing a subset. And so at best, we can estimate what that variance is. The reason why that's important, we're gonna table that until our discussion on Wednesday. But by and large, we're typically not conducting z-test because we don't know what the variance is. Since we don't know what the variance is, instead of a z-test, we use a blank test. Hopefully many of you can fill in the blank. What are we typically applying for comparisons of sample data? Thank you, Folarin and Nishal and others. We're going to apply t-tests, okay? And with that being said, there are also several different types of t-tests that can be applied. So first of all, the variance is unknown, so we know we need to use some form of a t-test. There are some additional caveats I'll introduce in a moment here, but if the samples are independent of one another. And so what I mean by that, let's think back to the example of observing 100 vehicle speeds, okay? Typically when we go out and we randomly observe 100 vehicles, it's likely if we did, the one observation in March of 2017 and another in January of 2021, it's probably reasonably safe to assume those samples are relatively independent of one another, okay? Now, there could be some variations there if we were observing speeds along the roadway outside of my house, as an example. Those may not necessarily be purely random samples. You may be observing, as an example, some of the same individuals, okay? And so there are formal tests that we can conduct to determine whether or not two samples are independent of one another. But in most cases, that's a relatively safe assumption. So if those samples are independent of one another and the variances are equal, we use what's referred to as Student's t-test, okay? If the samples are independent but the variances are not equal to one another, we use a very similar test that's basically identical in terms of how the test is structured. There's just a slight difference in terms of how we assess what the critical values are that we would compare our calculated t to. We can refer to that as Welch's t-test, or a t-test for unequal variances. And then thirdly, if those samples are not independent of one another, but they're dependent, we use what's referred to as a paired t-test, okay? And so in that example, we'll go back to the 100 vehicles. If we observe the same 100 drivers in 2017 and in 2021, we would probably find that there's dependence with respect to those data. And what I mean by that, if we looked at any individual driver, we would expect to see that some drivers tended to go faster than others during the before period and also during the after period. Okay, so during both time periods, certain drivers tended to go faster than average, and then there's other drivers that probably tended to go slower than average during both of those periods. Okay, and so if we ignore that fact, and we don't account for the fact that we have these trends within individuals, what happens then is all of that information is captured as just random noise. Okay, so we're not actually controlling for it. And so as a consequence of that, we're going to find that it's going to be more difficult for us to detect an effect or a difference if one even does exist. Okay, and so we'll go through some very interesting examples there to demonstrate when and where it's appropriate to look at a paired versus either the independent sample t-tests. Okay. And there are a few other caveats that we've not bothered with up to this point, but a lot of the statistical tests that we'll introduce in this course assume certain aspects about our data. And principally, one that comes up frequently is we assume that data are normally distributed. Now, if the data are not normally distributed, particularly if we have extensively skewed distributions, as we had talked about on Wednesday, then there are some potential concerns that arise because skewed distributions, to just recap from Wednesday, occur when we have a number of observations that are significantly larger or significantly smaller than we would expect just from random sampling, okay? And I think the best example that I can remember when I went through my statistics class myself is comparing incomes based upon graduates of a certain degree program at the University of North Carolina in the 1980s. And it just so happened that Michael Jordan, I guess I'm dating myself here because he's been retired for quite a while now at this point, but his income was significantly larger than everybody else that went through that program. And so as a consequence of that, that's probably non-representative. And the consequence of that, his income was so much larger, it would tend to shift up the mean income of that entire sample of alumni. And likewise, if we're looking at speed data, if we have someone that's just trying to see how fast they can possibly go and we clock them going 150 or 170 or whatever the case may be, they can skew that entire data set. They can increase the mean significantly larger than it actually is, just given the fact that it's just one observation out of 100. And so in those instances, instead of assessing differences in means, we can assess differences in medians as an example. And so there are a few tests that we'll refer to, and we refer to these generally as non-parametric tests. So a lot of the tests we apply, like the t-test and the z-test and so forth, make some implicit assumptions about how those data are distributed. We can basically apply these non-parametric tests, which basically don't have those same assumptions in terms of the distribution the data follows. But in doing so, we do tend to lose a little bit of power. And so what I mean by that, since we haven't introduced the term power yet, we would prefer to select tests that are robust. And so we would like a test is powerful if there's a high probability that we can reject the null when the null is actually false. And so that's a good property for a test to have. And so generally speaking, if our underlying assumptions about normality are met, we should use those parametric tests like the t-test, for example. If those distributions are not met, though, we would want to look to some of these non-parametric alternatives, which include, first of all, the sign test. We'll talk about this next week, hopefully, time permitting. In the sign test, all we're doing is we're comparing relative differences. So in the speed example, we observed the speed of 100 vehicles before, 100 vehicles after, and then we're just checking for those 100 vehicles in how many cases were the speeds higher versus lower in the after period after we sort those data in ascending order, for example. And beyond that, there are some more rigorous tests that are basically comparisons. They're analogous to students in Welch's t-test or the paired t-test, and those are referred to as the Wilcoxon rank sum and the Wilcoxon sign rank test, okay? So a whole bunch of information coming at you right now, but the one big takeaway from this slide is that we have a wide range of different test statistics we can apply in different settings, and we need to have some fundamental knowledge about when it makes sense to apply certain tests versus others, okay? And so once we've selected a test and we go through and we calculate the necessary descriptive statistics, we apply the test, we're going to compare our test statistic to a critical value. And what we'll find is when we set up our tests, we want to be very careful as to whether we conduct the test as a one-tailed or a two-tailed test. And so what I mean by that, at the onset of our study, we decide some significance level alpha that we're going to work with. So let's just say nominally 0.05. Going into that test, if we don't have any sense in advance as to whether we're going to see an increase or a decrease in whatever that parameter is that we're investigating, in the case of a speed limit increase, we would probably expect that speeds would go up. But let's assume we're focusing on some other type of policy where we're not necessarily sure what the impacts of that policy would be, okay? So if we're not certain, we'd want to be able to reject if we get extremely high values of that test statistic or extremely low values of that test statistic, okay? And so we're going to use a two-tailed test when we don't have a priori knowledge, so we don't have prior information that would suggest that we're probably going to see an effect that's in one tail of the distribution versus another, okay? So just there's some change that's been introduced. We don't know what the effects of that change are going to be. And so as a consequence, we would be interested in identifying extremely large or extremely small values of the test statistic, okay? And so stated formally, our calculated value, we'll just denote that as Z star. We're going to compare that to a critical value of Z. And in the two-tailed case, we would set this up if alpha is equal to 0.05, 2.5% of the distribution is less than this critical value and 2.5% is greater than this critical value. If we know going in that we're expecting to see a difference in one direction or another, so like I said, if we're assuming that speeds are going to increase, then we may be concerned only with the top tail, the upper tail of that distribution. And so we would be interested if our test statistic falls within this upper 5%. Or if we go back to the COVID example, maybe we expect that travel is going to be reduced. And so we'd be interested in lower values of those distributions. And so essentially we calculate our test statistic, we compare it to a critical value, which is going to be a function of whether or not we think there'll be a one-sided or two-sided effect of interest here. Based on alpha, we determine what those rejection values are, and then we check whether or not our test statistic falls within those rejection areas, in which case we reject the null. If we don't have a large enough value to fall into these regions, then we're not able to reject the null, and that basically means that we can't conclude that there is an effect of the speed limit increase or the COVID travel restrictions as an example, okay? And so to state that a little more formally, if our calculated value is beyond the critical value, we can reject the null in favor of the alternative hypothesis. So in our prior cases, that would mean we can reject the hypothesis that speeds haven't changed or travel levels haven't changed. Ergo, our conclusion would be then that we accept the alternate hypothesis, either speeds have gone up or travel has gone down or whatever the case may be. Now, if our calculated value is not beyond the critical values that were illustrated in the preceding figure, that doesn't mean that we're accepting the null hypothesis and we're just claiming that there's no difference, for example. The more appropriate way to state that is that we're unable to reject or we're failing to reject that null hypothesis. So it doesn't necessarily mean that the speed limit changes didn't have an impact or the COVID restrictions didn't have an impact. It's just simply based upon the data that we've collected, we do not have sufficient evidence to claim that there's an effect there, essentially, okay? It's not the same thing as saying there is no effect. So you just need to be very careful about overstating or understating the inferences we would draw from these statistical tests, okay? We'll circle back to that several times over the remainder of the semester. And as we saw before, when we're conducting those comparisons against critical values, we'll be using standard reference tables like the standard normal or the T distribution or F distribution and several others we'll talk about on Wednesday and in the coming weeks, okay? And then lastly, once we've gone through, we've conducted those tests, we've determined whether or not we need to reject our null hypothesis. As I had mentioned, failing to reject the null doesn't mean we're accepting it. And then beyond that, there are a few other important factors that you should take into consideration. Anytime you're conducting a research study or writing a research paper, it's critically important to provide the audience with context. And so to that end, are there limitations associated with your data? So back to my point about when the data was collected, where it was collected, how it was collected, so that the audience has knowledge of this. Because one aspect that's important for research is when we're presenting the results of a research study, we want to make sure that we're sufficiently clear that anybody else can repeat that same study and they would hopefully come to a similar conclusion there. But that's one of the important aspects of statistics, is we need to do a very, very good job of documenting how our study work was conducted and what any potential limitations would be. So maybe in the case of the speed limits, we were actually somewhat constrained there in that that was sprung on us very late. And so we only had a few months to go out and collect baseline data before the increases had gone into effect. And so in an ideal world, it would have been good to take those observations a year or 6 months in advance, but that was just kind of the nature of how that study was designed. And then is there any other information that would be useful or necessary? So there may be some unknown factors related to our study that we simply don't have knowledge about because we weren't there to directly observe them, or for whatever reason that data was not available to us. So just keep that in mind. In addition to reporting what you found, it's important to understand whatever limitations or unknowns there are that may potentially cloud some of those conclusions we reach in the end, okay? All right, so I believe we're to the last slide here. And so fortunately we've got 1 minute left, I guess. I just really quickly blast through this. But for Friday, I'm looking for everybody to identify 3 potential research topics of interest. And so for each of those topics, I want you to think about a different hypothesis or question of interest that somehow relates to transportation. And I just gave a simple example here. So what's the safest seating position in the vehicle? I want you to think about what type of data you would need to collect or measure in order to evaluate that hypothesis. And so in this specific case, that might be the number or rate of injuries that occur by seating position. And then thirdly, continuing on the preceding slide, what additional data would be useful for you to evaluate that hypothesis? So in addition to knowing what seating position a person was in, there's other factors that would affect injury, including age, gender, whether or not that person was belted, whether airbags were installed in the vehicle, etc. Okay, so I'm happy to chat further one-on-one if you want to get some ideas in terms of what's available out there. I'll try to put together a quick list of some transportation data sources as well that may help you to this end. But the goal is to get this submitted via D2L by the end of the day on Friday, okay? So with that, we'll continue talking about hypothesis testing on Wednesday, term paper due Friday, and then assignment 1, which should be out later today, will be due a week from Friday.